Hello and welcome to tutorial 7 for Applied Science 179. In this tutorial we will be dealing with the 4 fundamental subspaces, and we'll do a couple of examples to hopefully illustrate the whole concept and solidify it for you. So the first question we're going to do is we have this non-square matrix, and we're going to look at two non-square matrices to just try and hammer home the fact that they don't have to be square. Okay, so we are going to fill in this table below for this matrix A. Okay, so the very first thing we want to do is augment A with I, and then do Gauss-Jordan. Okay, so in this case, so we want to augment A with an identity, do Gauss-Jordan. We should end up with reduced row echelon augmented with our elimination matrix. Now, this one's not square, so we're definitely not going to find A inverse, and R is definitely not going to be an identity matrix. Okay, so this works fine for non-square matrices. It's just that we'll get reduced row echelon and an elimination matrix. Now, when you are augmenting your A, you need to pick an identity that has the same number of rows as A. Okay, and I'll show you at the end that will make all the multiplications work out, and that's the appropriate sizing. So let's get to it. We would do Gauss-Jordan on this thing. We already have a 1 in the top left corner, so we need to get zeros below it. That would include getting rid of or subtracting row 1 from that bottom one there, and that would give us this. So now we have a 1 in our second position there, and hey, this thing's already in row echelon, so that actually worked out quite beautifully. And now we need to get it into reduced row echelon, and so we need to use this one here to get rid of the 0 above it. Okay, because again, our goal is to get reduced row echelon form. So we'd subtract row 3 from row 2, and that would get us that. Okay, so that takes us all the way to reduced row echelon. We have reduced row echelon over here. Every row that's not a 0 row has a leading 1. Above and below each one of those leading ones are zeros. We've reached row echelon form, or reduced row echelon form. Okay, so that means we've made it. This matrix here is R. This matrix right here is E. And if I did this right, those should be sitting right down here. Okay, so there is E. A was our original matrix, and R was right here. Okay, so R, we have A, our original matrix, and E came from there. Now, of course, this allows us to do E times A equals R. So if we were to left multiply A by E, it should do all the Gauss-Jordan steps required to get us to reduced row echelon form. Okay, so that elimination matrix is going to do Gauss-Jordan. It's representing all the steps of Gauss-Jordan. Okay, so you'll remember that it's just slowly accumulating all those elementary row operations, and they get slowly accumulated into E there until all those row operations are represented by one matrix multiplication as shown here. Okay, so that takes us to E times A equals R. So let's just double check the sizing to make sure that's all going to work. So E was a 3 by 3. A was a 3 by 4. And we are going to end up with R, which is a 3 by 4. Okay, our two inner indices are 3, and our two outers are 3 and 4, and so those are, of course, what we end up with. Okay, so it all works out mathematically. That is the reason, or one of the reasons why we had to start with an identity that was only 3, a 3 by 3 identity. Okay, so that because in the end, our E is going to be a 3 by 3 elimination matrix, so that this whole multiplication works out. Okay, so we've made it to our E, A, and R, and we now have all the information that we need to find all of our fundamental subspaces. Okay, so the first fundamental subspace we're going to find is the column space. So, as with all of these, first off, we want to circle our pivots. So we go to our reduced row echelon matrix, and we circle our pivots. Okay, so there is 3 pivots here. The rank of this matrix is 3, and so the dimension of our column space will be 3. Okay, so there are 3 independent columns. Okay, so now, strictly speaking, by our algorithm, we would look at those 3 pivots. Those 3 pivots are the first 3 rows, and so we would come back here, and we would select the first 3 rows of A to form our basis. Okay, so that's reasonably straightforward, and that would give us a basis for our column space. Now, if you were super clever, which you all are, you would have also noticed that the dimension of this thing is 3, and that is the dimension of the space that this is sitting within. So your column space is sitting in R to the 3. So this matrix was a 3 by 4, okay, and therefore the column space is going to be size 3. So we're sitting in 3 space. There are 3 basis vectors in this column space, and so we could also use the standard basis. Okay, so the standard basis would be fine because the span of both of these 2 sets is identical. Okay, so in the case where the rank matches the size of the space, okay, and, well, if it's square, then it's full rank and everything's happy. In this case, the rank matches the dimension of the space that it's sitting within, and so a standard basis will be fine. Okay, the column space for A and R are identical in this case. Okay, but that's only because of those dimensions matching like that. Okay, so the safe thing is to just use those first 3 from A, but if you're able to recognize that, you can move to a standard basis, and it's just a little bit cleaner and nicer to work with. Okay, so for our row space, we again circle our pivots here. We have, of course, the exact same 3 pivots, which means our rank is 3, because it doesn't change. It was the rank of the original matrix, and that means we're going to have a 3-dimensional row space. Okay, that 3-dimensional row space is sitting within 4 space, right? Each one of these vectors is 4 long, therefore it's in R to the 4. We only have 3 vectors here, which means there's definitely going to be something sitting in the null space. Okay, but what do we pick as the basis for the row space? We just pick the pivot rows. Okay, so the pivot rows form the cleanest basis that we're going to get for the row space. Okay, so that's the most straightforward, easy one to grab. You just grab those 3 pretty vectors from the row space, or from the reduced row echelon form. Okay, so there's our basis for our row space, just those 3 vectors. Now, in the last one I said that there was going to be something in the null space. And there's going to be something in the null space because the row space and the null space are orthogonal complements, and they are both sitting within R to the 4. They're both sitting in the same space. In this case, it happens to be R to the 4. We had 3 pivots. Our rank was 3. So our row space was 3-dimensional. It's sitting within 4-dimensional space, which means there's still 1 dimension left over, and that's going to be taken up by the null space. Okay, so we know that there's definitely something sitting there. How do we find it? We want all solutions to AX equals 0. Okay, and so to do that, all we do is we find the homogeneous solution, and all we need to do is go to our reduced row echelon, augment with a column of zeros, and that is us having solved it. Okay, so then we need to get the parametric solution, and we will have the null space. So I've already thrown the reduced row echelon form over here. We augmented it with zeros, and I'm shifting it back into a standard format. Well, it's not standard form because I don't have all the variables on one side, but you get the point. Okay, so I've just taken this and moved it back into an equation type form. Of course, the -1 became positive on this side, and I have my 4 variables sitting there. Now, that, of course, is wonderful, but doesn't tell the whole story. We are missing something here, and the thing that we are missing is x4. So because there's no row for x4, x4 is still there. x1, x2, and x3 all have a pivot in their column, so they are all going to be our dependent variables, and we are going to take x4 as our free variable because there is no pivot in this column. There's not enough rows, we only have 3 equations, 4 unknowns, so we're guaranteed to have a parametric solution. So we have our x4 sitting over here. Okay, so x4 is our free variable. We assign a variable to it called t. That is our parameterization, and then everywhere we see an x4, we just slot t in there, and we are good to go. Okay, so then x is equal to this as a column vector, which is 0t minus 2t t. We could extract t. It's just a scalar, and we end up with t times this vector. Okay, of course t can be any value, and so this is a representation of span. So this is a span of this vector. So the answer is the span of this vector is the null space. So if the span of that vector is the null space, that vector would make an excellent basis. And so that is the basis for our null space. Okay, pretty straightforward and easy. Parametric solutions have to be able to do them. Okay, and then we have the null space of A transpose. Again, that would be the rows of E that correspond to rows of 0 rows in R. We have no 0 rows, and so it is just the null vector. The other way to get at that concept is that the rank, or both the null space of A transpose and the column space are sitting in the same space. They're both sitting in R to the 3. If they're both sitting in R to the 3, their dimensions of each of those two spaces are going to have to add up to 3. The rank of the column space, or the rank of the matrix was 3, so the column space was 3-dimensional, and so there's nothing left over. Okay, so they're sitting in R to the 3. 3 dimensions of that were used up for the column space. There is nothing left over. It is 0-dimensional. Okay, if it's 0-dimensional, it's just the 0 vector or the null vector, and it is a very boring space. Okay, so the basis for the null space of A transpose is just the 0 vector. Okay, and the 0 vector by itself is 0-dimensional because the span of it is only a single point. Okay, so we can just compile all that information into this lovely table here. Okay, so we have our E, A, and R up top here, and again, it's E times A equals R. Okay, so we look at A, we see that A is a 3 by 4 matrix, so M equals 3 and N equals 4. Okay, and so our column space is R to the 3. Okay, the columns are all 3 long, so it's in R to the 3. The rows are all 4 long, so row space and null space are going to be in R to the 4. Okay, so that's pretty straightforward. We know that these two are sitting in R to the 4, these two are sitting in R to the 3. If we know those two things, plus the rank, which we figured out by the number of pivots, we have 3 pivots, that gives us all of our dimensions at the bottom. So you can write those in before you even figure out what the basis is. And that's probably a wise thing, because it gives you a little bit of extra information as you're going into doing the actual basis writing. Okay, so if you're doing this as an actual question in homework, I would probably fill those numbers in first, because as soon as you get those filled in, it's just helping guide you to not make any mistakes later on the numbers of vectors or their lengths or anything like that. Okay, so this is in R to the 3. Each one of those vectors should be 3 long, and we should end up with 3 of them in total, or 3 dimensions. Okay, so the dimension of our column, so the rank of this matrix was 3, okay, and that is going to be the dimension of both the row space and the column space. So we can just write that straight in. We already wrote in what those two were, and then we can figure out the size of the 2 null spaces. So it's just going to be r to the 3, in this case, minus the rank 3, and so that's going to be 0. We have a 0-dimensional null space. It is just the null vector, just the 0 vector. Okay, and in the case of the row space and null space, they're sitting in r to the 4. The rank is 3, and so we have 1 dimension left over for the null space. Okay, and when we went and we actually found it, there was indeed 1 vector in our null space, or 1 dimension in our null space. Okay, so here are our 4 bases that we already found up above, and they've just been written in. But again, it's best to stick all those numbers in there first, because it just will help you to double check and make sure that you aren't doing something incorrect. Okay, so the length of these vectors should match the r the r space that they're within. Okay, and the number total of basis vectors that you have sitting there should match that number, and just remember that null doesn't count. Okay, so it's not going to count as a dimension. Okay, so the last one was non-square in having more columns than rows. This one is non-square in having more rows than columns. Okay, and we're going to go through the exact same process again, and yeah, just chug through that process. Okay, so first thing we need to do is augment with an identity. Okay, so again, remember what we're doing is we have A, we're augmenting it with I, we do Gauss-Jordan, and we end up with reduced row echelon and E. Okay, so again, the identity that you augment with should be sized according to the number of rows. Okay, and that's so that the multiplication at the end works out, and this is all going to work out. Okay, so we have our rows there. We've augmented. We have 5 rows, so we had to augment with a 5 by 5 identity. We then go and do Gauss-Jordan. Okay, so I already had a 1 up here. I use that 1 to get rid of everything below, and that should be sitting here. Okay, so there's that. We then are going to multiply that top row by -1. And once we've done that, we'll use the 1 that we just got here to get rid of everything below. So all these moves here. And we are now in row echelon. And we're going to use row echelon to now get us back into reduced row echelon. So we'll use this one. We'll use this one here to get rid of that one, and that one to get rid of that one. Okay, and so those 2 steps are here and here. Okay, so once we've done all that, we have managed to get to reduced row echelon. So we have the reduced row echelon sitting here, so that's our R. Alright, so this thing here is R. This thing here is E. And all the way back up here we had A. Okay, so those are our 3 matrices, and if I did this right, they should all be sitting right here. And there they are. Okay, so again, Gauss-Jordan's your friend. You run it through, you get E, A, and R. Once we have those 3 matrices, we have everything we need to figure out all of our fundamental spaces. Okay, so for the column space, first off, we should figure out what the rank is. So the rank of this matrix is going to be what? Circle our pivots. We have 3 of them. So the rank is going to be equal to 3, which means our column space will be 3-dimensional. Okay, so there should be 3 dimensions in our column space. This is a case where we cannot use R. Okay, so we cannot use the columns of R to do that. We need to go back to A. So we have 3 pivots there in the first 3 columns of R, and so we take the first 3 columns of A. There only happens to be 3 in this case, and so that's telling us that all 3 columns of A are independent of each other. and we need all three of them to form the basis. So those three vectors in A form our basis, which is sitting right there. Okay, so we take those three. That forms the basis for our column space. Dimension is 3 because rank is 3, and we have three independent vectors. So on to the row space. Okay, so the row space, again, rank is 3, we have 3 pivots. Okay, and we just take the pivot rows. So our pivot rows, we just take these 3 here, and that is just the standard basis. Okay, so that's kind of nice. That makes our life easy. There's a standard basis sitting here, and the standard basis is the basis for our row space. Oh, I should probably mention, as I'm doing all my row spaces here, I'm writing them as column vectors. Okay, that's just so we can jam it into that table in a more clean and easy fashion, and it doesn't take up as much space. We probably should put little transpose symbols there. It's not a big deal. I'm not going to be picky on that. Okay, so just concerned about what the vector values are. Okay, so in this case, again, it is a standard basis, and that is nice. Okay, null space. Okay, so remember the null space is sharing space with the row space. Okay, our row space is in R to the 3. Okay, our matrix is 5 by 3, which means that our row space is going to be in R to the 3. Each row vector is 3 long, so it's going to be sitting in R to the 3. Okay, so that's the basic, or the easier way to think about it. Each row is R to the 3, so it's sitting in R to the 3. The rank of this matrix was 3, and so how much do we have left over for our null space? 0. Okay, so it's 3 minus 3 is 0, so we have a 0-dimensional null space. It is just the null vector. Okay, so just the null vector sitting by itself, which the span of which, again, is just a single point and is 0-dimensional. Okay, so our null space here is pretty boring, just the null vector. But that probably means that the null space of A transpose is a little bit more interesting, which indeed it will be. Okay, so just straight off, we look at our dimensions. Again, this was a 5 by 3. Our columns are 5 long. The null space shares with the column space, and so we have 5 minus 3, a 2-dimensional null space of A transpose. Okay, so it's sitting in R to the 5. 3 of those dimensions are already taken up. It's mutually orthogonal, so it's only going to have 2 dimensions to take up. So our null space is 2-dimensional. We need to figure out what those 2 dimensions, or the basis for those 2 dimensions will be. And the process is we find the 0 rows in R, and the corresponding rows of E form the basis for the null space of A transpose. So quick and easy. We have them sitting right in front of us. We don't have to go through any extra parameterizations to find it. So the parameterized solution is just sitting there, and that forms a lovely basis for the null space of A transpose. Okay, so we summarize all that information into the table, and we are done. Okay, so again, this was a 5 by 3, so our column space and null space are sharing R to the 5. The rank of the matrix was 3, therefore the column space will be 3, null space will be 2. Okay, so our column space is 3, null space is 2. It was a 5 by 3, so the row space and the null space are sharing R to the 3. Okay, and our rank was 3, and so the row space is 3-dimensional, and our null space must then be 0-dimensional. Okay, so even without calculating anything, we know that thing's going to be a null space. Okay, so it's just the 0 vector. We then went and did all our basis work, and we can stick those vectors in here. The 3 as the basis of the column space come directly from these 3 columns. Okay, the 2 vectors forming the basis for the null space of A transpose were the 2 rows of E that correspond to the 0 rows of R. Our row space is the 3 pivot rows in R, and of course our null space is just that null vector because there was nothing left over for it. Okay, so we've done a couple non-square versions of this just to try and illustrate that they don't have to be square. Make sure that you saw both a null space and a null space of A transpose, and you'll be doing something very similar in your homework. Good luck. I'm sure it will go well. It's really quite straightforward. The big key is to just make sure that you get your Gauss-Jordan done properly and you get E, A, and R. Once you have E, A, and R, everything is easy from there on out. I highly suggest that if you can use a program like MATLAB or Wolfram Alpha, it's a great idea to just take E, A, and R and just play with them a little bit. So you can multiply E and A and see that it does indeed give you R. Yeah, throughout the course, I highly suggest that you put numbers into one of those. You have to do everything by hand because I can't give you a computer on the final exam. So you better be able to do it by hand, but it's a great idea to check your work with a computer and just get a chance to play with a few of these concepts using a computer, because it makes your life a little bit easier, makes it a little bit easier to test ideas and just run through a few extra examples. Good luck on your homework. See you in class.